If you're feeling the summer heat, you might be tempted to switch on the machine that makes all your problems go away. Your air conditioner. And the source of that sweet relief? Well, of course, it's chemistry. Air conditioners pull off the seemingly magical feat of making the air inside a home, car, or shopping mall deliciously chilly. Air conditioning, as well as refrigeration, which is the same thing just in a slightly smaller box, relies on the laws of physical chemistry. And PChem tells us that as a liquid evaporates into a gas, it absorbs heat. The molecules in a liquid are held together by weak intermolecular interactions. Not quite chemical bonds, just enough passing attraction to keep them from flying apart. Some of the molecules absorb enough heat energy, in other words, they get moving fast enough, to overcome these intermolecular attractions, escape, and take gaseous form. That's the reason you feel chilly getting out of the shower, and why we sweat to stay cool. The water has to absorb heat to evaporate, and it carries that heat away from you. An air conditioner's basic job then is to use a fluid called a refrigerant that constantly changes from a liquid to a gas and back to a liquid again to move heat from one place, like your sweaty bedroom, to another, outside, where it's already hot and miserable anyway, so who cares? Here's a admittedly very schematicified version of how most AC units work. The liquid refrigerant flows through a series of coils exposed to the air in your home. The refrigerant has a low boiling point, so the heat from the interior air is enough to make it turn into a gas, which means there's now more heat in the refrigerant and less in the air. A fan blows that colder air into your room, or straight into your face. We're not judging. So now your AC has to do two things. Dump the heat absorbed by the refrigerant outside, and two, it has to condense the refrigerant back into a liquid so it can be used again. And to do those things, it uses a compressor to ramp up the pressure on the gaseous refrigerant, so much that it can condense into a liquid again, even though it's at the warmer outside temperature. As it condenses, the refrigerant loses heat to the air around it, which another fan blows outside where it's already all sticky anyway. Which is a neat trick. Boiling something at a low temperature and then condensing it at a high one. Nothing in thermodynamics is free, and the compressor needs energy to do the work of compressing the refrigerant, which may explain your power bill in July. After the refrigerant condenses, the air conditioner backs off the pressure with an expansion valve so that the refrigerant can boil at the lower temperature again, which it does, in a loop, over and over, until your home reaches the temperature you set the thermostat to, or your housemates complain and switch it off because what are you, a polar bear or something? Jeez. While the refrigerant could be practically any substance, there are some chemicals that do the job better than others, and these refrigerants have a checkered history. A refrigerant needs to have a pretty low boiling point, and one that can be adjusted to where you want it by changing the pressure on it. It should also be pretty good at conducting heat and be able to absorb a lot of heat as it boils. And then it needs to be cheap, widely available, and as non-flammable and non-toxic as possible. That all kinda narrows your choices of chemical. Scientists thought they'd found the perfect refrigerant with Freon, which is the trade name of a group of chemicals called chlorofluorocarbons. But CFCs are actual murder to the ozone layer. They've been largely replaced with hydrofluorocarbons, or HFCs. HFCs don't damage the ozone layer, which is good, but they have a different problem. They're greenhouse gases. So the search is on to phase out HFCs too. Some alternatives? Simple hydrocarbons like these have been approved in the USA. Hydrofluoroolefins like this one are less rough on the climate than HFCs, but also more expensive. The most surprising potential replacement is CO2. CO2 totally works as a refrigerant. And even though it's the literal poster child for greenhouse gases, it's also way less potent than HFCs. Whatever we use in the future, it doesn't seem likely that we'll give up on AC altogether. Not in a scorching summer like this one. Pass the popsicles, would ya? Thanks for watching, and if you want to help us keep making great videos like this one, remember to subscribe, turn on notifications, share this video, and brag at your next cocktail party that you know all about the machine that's keeping everyone there from sweating their eyeballs out. We're pretty sure you'll go to cocktail parties, right? We'll see you next week.